Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the light emitting diode or LED. Let's start. By the time you finish this lesson, you will learn type of semiconductors used to build LEDs, light emitting mechanism in LEDs, ways to promote light emitting, and the relationship between the light wavelength and the band gap. From the previous lectures, we know that we can categorize semiconductors into indirect and direct. The way we put a semiconductor in a specific category depends on the alignment and misalignment of the maxima and minima of the valence and conduction bands in the K space. If you remember, I discussed this in detail in earlier stages in this course. A semiconductor is indirect if the maximum of the valence band does not happen at the same momentum the minimum of the conduction band locates in the K space. Therefore, when the recombination happens, the energy produced is mostly converted to heat. However, under some conditions, photons can be produced, however, with this disadvantage that the efficiency is small. A semiconductor is direct if the maximum of the valence band and minimum of the conduction band are aligned in the K space. In direct semiconductors, the energy released after the recombination turns into photons to a considerable degree. Of course, the recombination in direct semiconductors produces some heat too. In this lecture, you are going to take a closer look into light emitting or LED diode worlds and learn how an LED operates. Here I have a p-n junction diode, which is made of a direct semiconductor such as gallium arsenide. As I already mentioned, an LED emits lights during the recombination process. Therefore, it is logical to promote the recombination process in an LED to gain more light. Under no biasing in the equilibrium, you can find some electrons and holes that are drifting or diffusing and finally are recombining. But they are not enough for the production of a sensible light. When I talk about the light, I mean both the visible and invisible lights. Let's bias this diode forwardly and see what will happen. Under the forward bias, as discussed previously, we have extra accumulation of minority charge carriers at the edges of the depletion region. On the P side, we have lots of electrons, and on the N side, we have lots of holes at the edges of the depletion region. This is clearly shown in the minority concentration distance diagram. Now, think about it. The P semiconductor has lots of holes. Holes here are the majority charge carriers. Under the forward bias, the P semiconductor is hosting electrons injected from the N semiconductor. These electrons recombine with the holes in the P semiconductor, and guess what happens? Photons are generated. On the other side of the semiconductor, the same scenario takes place. The holes injected from the P semiconductor recombines with the electrons in the N semiconductor, and this produces photons. Now, a question that I can ask is, what can I do to promote the recombination process and therefore produce more light? Is there any way I can increase the area in which the recombination takes place and therefore the diode can produce more light? The answer to this question is yes. One way to do so is to increase the dopant concentration of the N semiconductor to a degree that I have to name the N region N++. If an N++ region is connected to a P-type semiconductor, the diffusion length in the P semiconductor increases. This increase in the diffusion length will result in the production of more light. So far, you've noticed how an LED works. But what about the wavelength of the light an LED can produce? What determines the color of the light if we are talking about an LED producing a visible light? Or what parameter causes an LED to produce an infrared or ultraviolet light? It is interesting that one of the main parameters determining the wavelength of the photon produced by an LED is the energy gap of the semiconductor used in the production of the LED. For example, to produce a red light, a band gap of 1.953 electron volts, green 2.206 electron volts, and yellow 2.12 electron volts is required. You may say, wait a second, the band gap of gallium arsenide at room temperature is around 1.42 electron volts. Does that mean an LED made of gallium arsenide is going to produce only a particular light with a specific wavelength? Well, this is a very good question. A simple answer to this question is no. Basically, what we can do is to manipulate the semiconductor and its manufacturing in a way we achieve the desired energy gap and therefore the desired wavelength. As an example, let's imagine we want to build a red LED using gallium arsenide. So I need to think about this LED structure. In the very bottom, I have an ohmic contact. Then I put a p-type gallium arsenide layer that acts as the substrate. Then I add a p-type gallium arsenide alloy that has 40% aluminum. On top of it, an n-type gallium arsenide alloy containing 70% of aluminum comes. This combination of semiconductor layers will give us a band gap of 1.953 electron volts and therefore the red light. In order to let the light produced to escape and get to an observer's eye, we must open up a window. To bias this LED, first I need to add these two isolation blocks on the top left and right of the structure, and then add the ohmic contacts. This is the window through which the light can escape. In this lecture, I discussed types of semiconductors we can use in manufacturing LEDs, light emitting mechanism and ways to promote light emitting in LEDs, and the relationship between the light wavelength and the band gap. In the next lecture, I will discuss photodetectors. Thanks for joining this lecture of Peacademia.